As we previously discussed, a quantum system is always in a superposition of its stationary states, each with a definite energy. The contribution of each stationary state to the superposition is determined by complex numbers known as expansion coefficients. The physical meaning of the expansion coefficients is closely related to the concepts of energy measurement and wave function collapse. I will now tell you about these concepts. Let's consider a quantum system described by the wave function psi, which is a superposition of stationary states psi1, psi2, and so on. These stationary states are characterized by their respective energies, E sub 1, E sub 2, and so forth, and are scaled by coefficients C sub 1, C sub 2, and so on, known as expansion coefficients. One might naively think that the expansion coefficient C sub n quantifies the proportion, or weight, of the stationary state psi sub n in the superposition. However, it is not that straightforward. The expansion coefficients are generally complex valued, and therefore cannot directly represent proportions. The proper proportions, or weights, of the stationary state psi sub n in the superposition psi must be real, positive, and add up to 1. As you will see from the exercises for this lesson, the quantity that satisfies these conditions is the squared modulus of C sub n. This quantity, which is also the product of C sub n and its complex conjugate, represents the proportion of the stationary state psi sub n in the superposition psi. Indeed, this quantity is clearly real and positive. As for the second condition, you will be guided through a calculation that demonstrates the sum of the squared moduli of the expansion coefficients equals 1. This result follows from the normalization condition, which requires that the spatial integral of the squared modulus of the superposition wave function psi is equal to 1. What is the physical significance of the proportion represented by the squared modulus of C sub n? How does this proportion manifest in experimental interactions with quantum systems? The answer to these questions is closely tied to the process of measuring the energy of a quantum system. Let me tell you how it works. Unlike in classical physics, the result of a single energy measurement on a quantum system in the superposition state psi is not deterministic, it is inherently probabilistic. Additionally, the measurement device will yield only one of the specific values, E sub 1, E sub 2, and so forth, corresponding to the energies of the stationary states that make up the superposition psi. Each possible outcome of the energy measurement occurs with a probability given by the squared modulus of the corresponding expansion coefficient. Let me present the following diagram to illustrate this important concept. Consider our quantum system just before the energy measurement. It is in a superposition state described by the wave function psi. Now, let's perform an energy measurement on the system. The specific details of the measurement process depend on both the system and the apparatus, which we will not explore here. For simplicity, we'll treat the measuring device as a black box and assume that the measurement occurs instantaneously. The outcome of the measurement is intrinsically uncertain, with several mutually exclusive possibilities. One such possibility is that the device will display the system's energy as E sub 1, which corresponds to the energy of the stationary state psi sub 1. The probability of this outcome is given by the squared modulus of the corresponding expansion coefficient, C sub 1. Another crucial aspect of quantum measurements is that the state of the system immediately after the measurement is not the same as the superposition state psi before the measurement. The measurement process inevitably alters the system's state. In the scenario we are considering, where the energy measurement yields the value E sub 1, the measurement changes, or, as it is often said, collapses, the system state to psi sub 1, the stationary state corresponding to energy E sub 1. Obtaining E sub 1 as the outcome of the energy measurement was one possibility. Another possible outcome is E sub 2, which is the energy of the stationary state psi sub 2. The probability of this outcome is given by the squared modulus of C sub 2. Consequently, the state of the system immediately after the measurement will be psi sub 2. Similarly, the energy measurement might yield the value E sub 3. The probability of this outcome is given by the squared modulus of C sub 3. In this case, the measurement would change the system state from psi to psi sub 3. This pattern applies to all the stationary states that make up the initial superposition state psi. It is evident from this discussion that the result of an energy measurement can be known with certainty only if the system is in a stationary state right before the measurement. In this scenario, the measurement is guaranteed to return the energy of that stationary state, and the measurement process will not alter the state. In a generic case, however, where psi is a superposition of several stationary states, an energy measurement returns the energy of one of these stationary states psi sub n, and collapses psi onto psi sub n.